Hello guys, can you hear me? How are we doing? Are there any questions before we get started? All right,
Professor,
yes.
Question about the homework. For 1610, were we supposed to show, construct a function, or was it enough to show that the cardinalities are the same?
Switch over, I want to look up what it says.
Uh, 1610b.
I mean, so to show that the cardinalities are the same, we would have to construct functions or use a result that we proved in class, which ultimately involve construction of function.
But we have to like write out the function. We can't just be like, because we showed it in class.
Oh, yeah, I mean, sure. If so, you're more than welcome to use things that we have shown in class. Just say we showed it in class.
I see.
But then you have the function, right?
Right.
So whether you, I mean, alternatively, you could just restate the function from what we had in class.
Okay. All right. Thank you.
Yep. There's always this discussion about how many details should one include in answers, and I mean, you are more than welcome to use stuff that we've done in class. You can either restate it, or you can say that we did this in class at some point. I should also say that when you see my exam questions, there are no trick questions on my exams. So we'll talk more about that when we get closer, but you will see, you could very well see a question of this sort on an exam, and then it will say like, give me a function that is that goes from one set to another set, which is onto, and it can very well be that this is exactly a question that you have done in the homework or that we have done in class. And then if you're asked to provide such a function, you're more than welcome to use exactly the same function as what you did in the homework or what we had already done in class. So there are no trick questions in my exams, and the same thing in the homework. It's not, this class here is not going to be about creating tricks and stuff like that. If there's a difficult question, I'll flag it and say that this is hard, like with the optional problems that are being put on the homework. Okay, anything else? Otherwise, we need to finish up. We're running a bit behind what I had in mind. So today we're going to do more like, we're going to follow the textbook a little bit closer. I had a few things prepared for the end that are not in the textbook, but I want to get through some of the theorems that we have used in class and we talked about, and maybe try to write some of the proofs down. So one of the first theorem that we're going to be looking at is if I have a sequence of real numbers and say that xn converges to L, which is also a real number. Right, so we have a sequence of real numbers, it converges. So say that this is the case, well then this sequence here is bounded. Then xn is bounded. these are things that we have talked about a number of times. And what does it mean to be bounded? Well, my job is to find a very large constant, find a humongous constant such that when I take the supremum of, what we need to do is we need to show that the supremum here is finite. We want to show that the supremum of the absolute value of xn is finite, right? Then you're bounded. Bounded here means both from above and from below, and this is ensured by taking absolute value. And the way that we go about doing it is, because it converges, we can control the tail of the sequence by L. So because it converges, we know we can find, give me any epsilon, I can find an n such that when I'm bigger than that number, the distance between x and its limiting point is going to be very small. And so let me just pick epsilon to be 1, right? So here we use this epsilon to just 1. I can do this for anything, and here I just choose 1. Okay, so this is going to give me control over the tail, all those n's that come out in the towards the end. And so then I will then write xn as xn plus L minus L, absolute value. I'll use the triangle inequality. I'll say that this is less than xn minus L plus L. And the first one here, this is small. This is bounded by 1 plus L. And this is going to be true for anything that's coming out towards the end. And then, so how do I get the supremum to be finite? Well, I'll take then xn is going to be less than the maximum. And now I'm going to write max instead of supremum. Xn is going to be less than a maximum of the first one. So this will be x1, x2 up to xn. Right, that takes care of the first elements, and then this part here takes care of the latter ones. So here I'll put 1 plus absolute value of L. So then if I take supremum on the left-hand side, it's bounded by this constant here. Right? And this constant is finite because I'm taking the maximum over a finite number of points. And so the supremum is finite. Right? So if you converge to a real number, you're bounded. But of course, the other way around is not true. Like we have seen examples of bounded sequences that are not convergent. Any questions on this slide? That wasn't so bad. Another thing that we have talked about, we have seen examples and counterexamples too, is when you work with these limits, how do you manipulate them? So again, if we say we take two sequences, so let me take an, this is a sequence inside R, we take bn, another sequence inside R. Let's assume that an converges to a number in R, and bn converges to b in R. Then what I want to know is, how can I manipulate these things? So here I have two sequences of real numbers. I assume that both of them converge to separate numbers a and b, and how can I manipulate them? Well, the first one is that if I take a constant, say a real number, it's true that if I take the limit as n goes to infinity of the constant times an, this can be computed simply by taking c outside, and then I'll get my a. So that's possible. Keep in mind here we're talking about limits that are in R. we're not allowing here for, we're not allowing the sequences to converge to plus and minus infinity. If I take the sum, so if I look at the limit of an plus bn, I can split it, and this will just be the limit of a n as n goes to infinity, as well as the limit of bn as n goes to infinity, and it breaks up into just into the sum. The third one is if I multiply, if I take the limit, the product an bn, it has the same property, that this is just going to converge to the product of the two limits. And then finally, the last one is when we take a ratio. If I look at the limit of the ratio of an divided by bn, this here is equal to a divided by b when b is not 0, right? We have to make sure that we don't divide by 0. So the limits behave not, I mean, it is linear, right? You take constants outside, you can add, but you also have properties with the product. So the product behaves nicely and the ratio behaves nicely, provided that the thing that you divide by doesn't go to 0. And just to reiterate, some of the things that we have talked about in particular last time is that if you take an to be n and you take bn to be minus n, this is where it gets to be problematic. Like I could be interested in taking this one here. Like I will not have that the limit of an plus bn, like these add up to 0, right? So I'll have that this is equal to 0, but this here is not equal to, the limit of an plus the limit of bn, right? Because these are undefined. Like this quantity here, this is plus infinity, and this quantity here, this is minus infinity, and we do not have any meaningful way of assigning value to the difference between plus infinity and minus infinity. Another thing to look out for is this thing with the 0 down here. You should also be careful down there. It is not as bad as this one here, but yet if you look at, if you instead of these ones up here, you take an to be 1 over n, we looked at that a number of times, and you take bn just to be what it was up there, so take it to be n. In that case, right, the an's converge to 0, so we have to be careful when we divide. And if I look at the limit of an times bn, well, in this case, an times bn is exactly 1, right? So the limit will be 1. But you could also try to break it up. So you'd have that this would be the limit of an times the limit of bn. And the limit of an, this one here would be 0, and this one here would be plus infinity. So be careful, because of some textbooks define 0 times plus infinity to be 0. And so if you do that, if you also do that, this thing here doesn't work. You don't have this property that 1 is equal to the limit of an times the limit of bn. So you don't have this property, because this one here would be 0, and this one here would be plus infinity. And if your definition is that this is equal to 0, you have a 0 on the right hand side and you have a 1 on the left hand side. So if you have a textbook that does stuff like this, or if you read a paper, or if you read something online on a math website that discusses various things, you will see this convention here. But then just be careful whenever you apply such limiting operators, because if you end up in this situation, you will not have this property that you can separate them out like this. And the final thing I want to say is that so when Bn converges to 0, when Bn converges to 0, well, then you often need L'Hopital and better. And I'm hoping we'll spend some time doing this. So better Taylor. When you compute the limit as let's say n goes to infinity of an over bn. Like I think last time we had an example where we looked at, we had this function f of x. I remember writing this up on the board. Right? And so if I were to look at x's behavior around 0, then I would have a 0 over 0 situation, right? So I wanted to look at the limit as x goes to 0 of f of x. So how would I do it? This would be sine of 0, 0. I divide by 0, so I need L'Hopital. And one way to do L'Hopital is to look at when you have a 0 over 0 situation. I'm hoping everybody has seen L'Hopital sometime in your life. Is that correct? Have you all seen L'Hopital's rule in one form or shape or another? Or you've all seen L'Hopital's, I think there's an S there, L'Hopital's rule. Right, so you take the derivative of what's upstairs, right? So you get something with cosine, and the derivative of x is equal to 1. And then you get that cosine at 0 is equal to 1. So you get this property here. So when the thing downstairs goes to 0, then typically you use L'Hopital's rule. But just to preempt it, I also use the word Taylor here. And the reason I'm saying that is because some of us, I have seen students that are just to get this ratio, and then they get very eager to use L'Hopital's rule. So just to maybe put a teaser out there, let me just show you the last homework that I posted out there. So let me try to share the screen so you guys can see what I'm talking about. So the homework number 4 is all about computing these limits of various forms and shapes. But I put an optional problem here, this one here. So you have sine x to the power 100. And this problem here is created such that if you try to apply L'Hopital, you're going to have to apply L'Hopital 100 times. And so this should give you a sense of that maybe L'Hopital is not the way to go about doing this. And so see if you can apply L'Hopital 100 times, right? But you're going to have many sheets of paper by the time that you're done. Or you could try to find a smarter way of doing it. And so this is an optional problem. You don't have to solve that now. I'm hoping that at some point we'll talk about Taylor's formula. And this problem here, this is really a Taylor's formula problem. It is a much better way to do this than L'Hopital. But if you have been used to seeing problems of this sort where you get a ratio like this one, then we hit it with L'Hopital, and this is fine. But sometimes you can end up in real trouble because you just have to keep doing it. You end up with the next situation and it's also a 0 over 0, and then the next one is a 0 over 0, and the next one is a 0 over 0, and it just keeps going like that. Then maybe L'Hopital is not the way out of the hole. So I'm hoping we can do something with Taylor at some point and show you guys how to do that. Okay, so we have the theorem, and we're going to prove it. The proof is not so bad. The proof is not so bad. Let me just maybe show some of the ones that are a little bit harder. If if we looked at, for example, number 2, this is a little bit trickier. If we did number 2, we could, what is it we know? We know A and B are limits of AN and BN. So if we did number 2, we would have that I can find an N1 such that the difference between AN and A is small, say smaller than epsilon over 2 for any N that's bigger than this N1. And I can do the same thing for the BNs. So I can find an N2 such that the difference between BN and B is less than this epsilon over 2 for any N that are bigger than N2. Right? I can do this for any epsilon, so I can also do it for epsilon over 2. And then we combine. So this is a typical thing. So our job is to find an N that will make this the sum of AN plus BN close to A plus B. And so if I set N to be just a max between these two, set N to be this maximum, then I should have it. Because then if I look at AN plus BN minus A minus B, I want to make this small. I'll use the triangle inequality, and this will be AN minus A plus BN minus B. And when I have here that N is bigger than capital N, it means that in particular it's bigger. Particular is bigger than N1 and N2. So I have these bounds up here. I'll get here that this is less than epsilon over 2 plus epsilon over 2, which is my epsilon. So that worked well. For number 3, when you have the product, there's a way to break these products up that I wanted to show you. So if I say here, let me give the proof in the case that A is not 0. So we'll do the case. So assume here that A is not 0. Then you can try A being 0 yourself, or maybe we can do it in the end. So the result doesn't require A to be non-zero, but I'm going to give the proof in that case because we're going to be dividing by A. So what I want to do is, I know I can find an N1 such that Bn minus B is small. Okay, so I want to have it smaller than the absolute value of A times epsilon over 2 for any N that are bigger than N1. And likewise, I can also squeeze AN and A together, so there exists another one such that AN minus A is smaller than, I think it is what, 1 divided by, let me call it M epsilon divided by 2, where M is the supremum over the B's. Right, and we know that Bn is a convergent subsequence, so I know that this supremum here is finite. This is what we just did on the previous page. So I have these, I can find these bounds. N here is bigger than N2, and as before, we put N to be the maximum. And I'll just check that it works. And so it's this decomposition that is coming now on the next slide. This is something that people have used. This is something that people have used in other contexts as well. So this way of decomposing it, this can come in handy for you in other situations too. So you write your AN BN minus AB. The way to break this thing up is by saying this is AN BN and then minus, and then you do a mixture. You do an A times a BN, and then I need to add it back in A BN and then minus AB. Like I did nothing else and add and subtract the same thing. And it's this mixture that's going to make everything work. So then I'll go about it. Here in the first one, I can put BN outside. And then the last two terms, these two AN and BN, AN and A, I can put those together, right? So that was triangling inequality on the first one. It's going to give me the inequality. And then the same thing for the other one. There, the common factor is A, and then Bn minus B. So the Bn, this is what is controlled by M. That was the supremum. So if I take the supremum here, I'm going to get something that's bigger. And An minus A, this was controlled by 1 over M epsilon over 2. And then the other one was A. Okay, so that's there. And then the difference between the B's, this was controlled by 1 over absolute value of A times epsilon over 2. And these coefficients up here, you of course picked such that everything cancels out neatly here, and you're going to get an epsilon. This was in the case that A here was not 0. So if A was 0, we also need to do that case. So if A is equal to 0, the story is almost the same, but not quite. Then what would I do? I would take An, Bn, right? So now I'm claiming that this converges to 0. So I need to make that thing small. I'll do a similar decomposition as before. I'll have An and then Bn minus B plus, and then I need to make the equality sign true. So I'll need to have An, B. So it's the similar decomposition as up here, but now we're just using that A is equal to 0. And I do that because I cannot really have this 1 over A here when A is 0. And then inequality it out in triangle inequality. This here is less than the supremum over An times Bn minus B. And the other term would be B times An. But I know that this term here, this goes to 0. And I know that this term here, because A converges, A is equal to 0, so An converges to 0. So this difference, these differences, this difference here goes to 0. This one here is finite because An converges to 0. So this was just that little detail here in the end. But what it shows is that products, they also converge. Any questions so far? The last one is the more tricky one because now we're dividing by B. And so dividing by B, division is always difficult. So we'll show the implication that when Bn converges to B, which is not 0, then that implies that 1 over Bn is going to converge to 1 over B. Right, and then we just use the previous one. Then we just use the previous one because then we have that you can multiply and then you will still converge, and then use then 4 follows from 3. So how do we show the implication? Well, it's trickier now because we cannot just bound, like, we know that the Bn's this is a bounded sequence because it converges, but this is not enough, right? That's not what we're interested in here, because if I make this thing bigger, I'm going to make this thing here smaller. Right? So the inequality is now going in the wrong direction. So the key is to use that it converges to something that is not 0. So let me try to explore that. And, so first we're going to show we claim, so there's a little claim here. I know that Bn converges to B. Okay, so now I'll take absolute values. So the claim is that the absolute values, they will also converge. And so how would one prove this claim? Like, I know that the B's converge to B. How do I get that this thing here then also converges after I take absolute values? It's not so bad. It's again an exercise in the triangle inequality. You take Bn and you write it as Bn minus B plus B. And then you use the trialing inequality. And what you do is you move this thing to the other side. So you show that when I move this to the other side, here I have bn minus b. Right, so this goes to 0. Therefore, this difference here is bounded from above by 0 in the limit. That gave us 1. We also need the other one. The other one is not too bad. I just switch the roles. If I do b, I can write this here as b minus bn plus bn. Use the trial inequality. This is b minus bn plus absolute value of bn. Now I'll move bn to the other side. So I'll get the absolute value of b minus absolute value of bn. This is now bounded from above by b minus bn. Right, and I also know that this converges to 0. So now I have that both the sequence and minus the sequence, both of them in the limit, are bounded from above by a 0, and therefore the claim follows. Right, so this here all implies that the absolute value of b minus the absolute value of bn in absolute value goes to 0 as n goes to plus infinity. So that was the first step. So what this shows is that so bn converges an absolute value to b. So in particular, right, this is a positive number. So if I cut the positive number into 2, I can find an n1 such that for any n that are bigger, bn in absolute value are going to be bigger than, say, absolute value over 2. Right? If this here is equal to 1, then when I converge to 1 in absolute value, I know that these absolute values are going to be bigger than a half after a certain point. And this is what allows me to control with this division here, because now I'm bounded away from this 0, which is the problematic part. That was one n, and then I'll find the other one. The usual way. I can also find an n2 such that for any n bigger than n2, when I'm looking at the distance between b and bn, I'll get something that is smaller than, say, epsilon absolute value of b squared divided by 2. Again, these constants here, they look funny, but it's created such that when you plug it all in, it simplifies out to being something really, really simple. And so for n bigger than that maximum as we've had before, n1 and n2, what do we have? We look at the difference. The claim was this thing here is going to be small. And so we merge the two ratios into one, we put them on common line. So we need to multiply here. I'll have b bn. So upstairs I'll have a b there, and then I'll have a minus bn there. Take absolute value. I can plug absolute value. This is going to be b minus bn divided by absolute value of b times absolute value of bn. And then I use these right-hand sides up here. What's upstairs, I'm going to make bigger. So what's upstairs, I'll make bigger. I'll write this as epsilon absolute value b squared divided by 2. What is downstairs? Well, what is downstairs is the absolute value of b, and then I'll divide by something that is smaller, the absolute value of b divided by 2. And if I've done it correctly, everything should cancel out, right? And I'm going to get an epsilon here. So you see the key components in all these proofs is that the key step in all these proofs is to recognize a way to break this, so you can start using that you can control the distance between an and a. This of course varies on the thing that you're trying to prove, but you're trying to do that, and the trial inequality is always being used here. Okay, so these properties, you know, how to operate the limit, you're not surprising, but it's kind of nice to see the proof perhaps detail. Any questions on this part? Any questions on this part? So there are other properties too. There are other properties too. Which we have, so again, like my AN is going to converge to A, real number. BN is going to converge to B, real number. So other properties would be like, if I know that, say, the ANs are positive. If the ANs are positive, well, then the limit is going to get to be non-negative as well. There was a question in the chat. Okay, so let's go back and have a look. Well, so it's this is the question, right? I know that my BNs in absolute value converge to B. So, right, and I know that B in absolute value is strictly bigger than B over 2, which is strictly bigger than 0. Right.
So I see. So that's the reason why you like make the absolute value of Bn is over like the absolute value of B over 2, right?
Yes.
Because you want to make sure like the I see. Yeah, I'm just curious why you suddenly just like over 2.
Well, but that is just a choice, right? If you don't like the 2, it's because I know that. Okay. That's
also like the it could be like other numbers as long as the B is like the absolute value is over B something.
17 could also work.
Oh, okay, I see.
But you cannot put 1.
Yeah.
You cannot put 1. It has to be bigger than 1, right? You could put
you
17.
just want to make the. Oh, I got the answer. I got the reason why you make the 2 here. Thank you.
It doesn't have to be 2. You could also put 17. And if you put 17, then you put 17 down here as well.
I see.
Just don't put 1. 1 is not going to work, right? Because you know you converge to absolute value of B. So you do not know that at some point you will be strictly bigger than, right? This would not work. You need something here that is strictly bigger than 1.
Got it. Thank you.
Okay. I'm going to switch it back to 2s. Yep. Other questions before? I don't want to. I mean, if you don't stop me, I'm just going to plow through all of this. So please just stop me and ask questions. We were trying to look at additional properties. So you down there. Right. So if my elements in the pre-limit, right, so this sequence here, if they are all non-negative, then the limiting value is also going to be non-negative. And you can also say that if AN is less than BN for all n, well then A is going to be less than B. The last one, this is number 3 that I wanted to mention. This is called the squeeze. It's not how you spell squeeze. The squeeze or the sandwich. the squeeze of the sandwich theorem. It says that if you stick something in between, so if Cn is another sequence, so we're not making any assumptions here about it converging, right? But what we're going to say is that it's sandwiched in between these two. The sandwich in between these two, then Cn converges. Then if these two limit points A and B up here are the same, then the CNs also converge. So the sandwich in between two convergent sequences, you're going to be convergent, and the limit is exactly what you had before. So might be easy to believe stuff like this, but just another note, and the example we have seen many times is if I looked at an to be 1 over n, this is strictly positive. But when I'm looking at the limit, I'm going to get a 0, right? So it's not going to be the case. It's not going to be the case that if you have something that lives between 0 and infinity, this does not in any possible way imply that the limit point belongs to and then that's the example, right? 1 over n, all of them belong into this open interval. However, the limiting point does not belong to the open interval because it's equal to 0. So these greater than or equal to sign here, this is important. You cannot put greater than over here. This won't work. This is an exercise. You can, if you're interested in seeing it, you just Google for squeeze or sandwich theorem related to convergent sequences, and there'll be lots of references for this. Are there any questions before we move on? We're closing in on the first big result in this section. The where we've been today, and also last time, and even the time before that, is in the early sections of where is the table of contents? There's the table of contents. Right, we are in here. We're working with sections 1 up to section 2.4. Right, monotonicity was last time we talked about this. We are now punching into this 2.5, and you can see here in the first section, right, there are lots of things being listed, but you see Cantor's theorem, right? So that's a big gun. And the same thing when you come down to here, you'll see the Bolzano-Weierstrass theorem. That's a big gun. So we're now honing in on the biggest result in section 2, and this is this Bolzano-Weierstrass theorem. So we're going to try to see if we can, I don't know if I can get through it today, but that's the next, and this is so that's the big gun in section 2. It's that one there. Just as Cantor's theorem in the first chapter was the big pearl. So we're moving into section 2.5. And some of the things that are in there in the beginning, we already talked about. Like, so we already talked about that if you ever see a sequence, right? So this is a sequence that is indexed by natural numbers. This is a sequence of, say, reals. Some of you came to office hours, and a fancy way of writing this here is also just to say that this here, we could call that for, I don't know, A. Right? So a fancy way of writing that could be that A belongs to R to the power n. So this is a function So you can think about A as being a function that goes from N into R. And so normally when we write functions, you would write A of N. But when you do sequences, that's not the notation people use. You put the N downstairs. So that's one way to think about it. Another way that we ended up talking about is that you could also think about this A here as being like a humongously long vector. You could think about this as being A1, A2, A3, and then all the way down, and it just keeps going. These are just, it's just different notation for writing the same object. It's a sequence, it's a string of real numbers that are indexed by the natural numbers. So that's a sequence. We spent quite some time talking about sequences. We also mentioned that there's something called a subsequence. And now we're going to be talking a lot about subsequences. So a subsequence, this is an A, N, and then there's another one down here, K, A, N, K, right? And now the index that is running is K. So this is a subsequence, so it's inside that set AN. This is a subsequence. So it's just a subset of the original subsequence. So let's do the example we had. I think we had that one already in class. If I looked at the original sequence being -1 to the n, so A1 would be -1, A2 would be 1, A3 would be -1, and so on. Then what I could go about doing is I could say that N1 is going to be, say, the first one. Then I'll have N2 will be the third one. N3 would be the fifth one. Right, so we note here that Nk is bigger than or equal to K. Right, 3 is bigger than 2, 5 is bigger than 3, and so on. And in that case, A and K, that subsequence, it satisfies that A and K is equal to -1 for all elements. Because what I'm doing is I'm picking out all the minuses in the original sequence. And so in particular, so while AN does not converge, ANK does, right? And the limiting point is of course going to be -1 because it's just a constant sequence. So that's what a subsequence is. It's just a subset of the original sequence. And then some properties. Some of the first properties that we're going to see is, well, limits are unique. I think this can be no surprise, right? If a sequence converges, it converges to exactly 1 point. It doesn't converge to 2 points. One thing about the subsequences is that if AN converges to A, then any subsequence, any and all subsequences, then any subsequence, so let's call that for A and K, and any subsequence also converges to A. Right, so limits are unique. So that A here, this is a unique quantity. How would one go about seeing that? I mean, it's, yeah, I don't know. Maybe, how would one go about seeing number one, for example? Well, if AN converges to both A and AN converges to B, well, then what? Well, then I can make the distance between these two small. Let me make it smaller than 1 over m. I can make this small. I can make the distance between AN and B small. By choosing n sufficiently large. And then what? Well, then I'll use the triangle quantity again, A minus B. I can write this as A minus AN plus AN minus B, same trick as we've seen before. I'll now use the triangle inequality. I get a greater than or equal to, right? And then these two here, they're bounded by 1 over m each. So this is bounded by 2 over m. Right, so now we take the limit, pass m to infinity, and what you see here is, you use a squeeze theorem if you so desire. You'll see that a minus b is less than or equal to the limit, which is equal to 0. Right, so a and b are the same. So the limits are unique. This can be of no surprise. Any subsequence converges to the same thing as the original sequence converges to. How would one see that? How would one see that? Well, what would happen is that, right, so for any epsilon bigger than 0, I know I can find a number in the natural such that when I'm later than that number, AN is less than epsilon. But then I use this property that if I'm a subsequence, because nk is bigger than k, and that was that property we had. That was that property we had. That was that property we had somewhere, right? That was right there. That if you're a subsequence, then the indices in the subsequence, these come no earlier than the original indices. So that means that when I'm past n here, I'm gonna get the same property. I'm gonna also have that ANK is less than ANK minus A is less than epsilon for any k that are bigger than n. Right, and that was the conclusion. It's simply because having this property here, this is stronger than having this property here. Right, because these nks here, they come later. Right, so this, when I'm n is above a capital N, so I just need to check it here for k's. I don't need all of them. I just need I would have this property here with AK minus A. This is true for any k bigger than n, but I only need it for the nks, and those are fewer. So if I have a subsequence of a convergent sequence, there's really nothing new there. It will converge to the same thing. But of course, this example, this is why this example is here. It shows that subsequences do have something to add, and they do have the potential to have limits, even when the original sequence has no limit. Okay, so that was a little bit about subsequences. Are there any questions before we start on this Bolzano-Weierstrass theorem? Like in this course, a big thing that's coming might be the next chapter where we're already getting into, it's this word topology. So I'm going to try to cast some of these concepts that we're talking about using the terminology already in section 3. And so when you talk about topology, it's all about talking about balls. And there are many kinds of balls in this world. You can have round ones, you can have square, triangular, diamond shape. There are lots of balls available. We had talked about that a while back, but let me do a little bit more of it. So there's something called limit points. This is what our textbook calls it. When I went to school, it was not called limit points. It was called cluster points. And there are still some people that call it accumulation points. They all mean the same. They all just different words for the same thing. This is what our textbook calls it. And because I grew up calling it a cluster point, I will be saying the word cluster point. So what is a cluster point? It's these -1 and +1s from that sequence that we had before. But we had that sequence that will alternate between 1, -1, 1, -1, 1, -1. The two cluster points for that sequence are 1 and -1. So how do we define it? Well, you take a point, and it's called A, and then you put a ball around it. I'm going to illustrate these balls here by actual circles. Right, so A here is supposed to be the center. A here is supposed to be the center. And then the diameter is supposed to be epsilon. Right, so an epsilon neighborhood of A, so this is a ball. So this word neighborhood, an epsilon neighborhood of A is what? This is denoted by V epsilon of A. So it's those points in, say, Rn, such that the distance between the distance to A is less than epsilon. I should say here that this one here should more properly be called an open neighborhood, but for now let's just call it a neighborhood. So it's just a ball. The ball defined with strictly, the word open here has to do with this thing here being strictly less than epsilon. This is in Rn, so in R, these balls, they are different, and you don't circle around, right? Such a neighborhood would be nothing else than just an open interval, A minus epsilon to A plus epsilon. And so we can recast the language that we have had. We can say that An converges to A if for any epsilon bigger than 0, I can find an n such that when I'm later than that n, I'm in this neighborhood. An is in A's neighborhood. So for any epsilon, so any neighborhood around A, the sequence is eventually going to be in there. That's the language. So An is eventually in any neighborhood, in any ball, around this limit point. So this is again a new word, eventually. So we have a bunch of new words. You might have a limit point, cluster points, accumulation points, neighborhoods, and eventually. And when I went to school, this was not called eventually, this was called after a certain step. After a certain step, and that step is capital N. So after capital N, all the later points in the sequence, they belong to that ball that's sitting around A, right? So what happens in the picture is that you have your A1, you have your A2, you're filing around out here, right? That's your sequence, you're popping around. If it is to converge to A, what it means is that you pick a ball, put it around A, at some point, these points here, you're gonna come inside. Right, so there might be A17 is coming in here. And then, well, it could stay inside, it could also go out, but eventually it's going to stay inside. And this is true no matter how small you make the ball, no matter how small you make the epsilon. So it keeps spinning around in here. Right, so eventually, any ball is going to contain AN. So that's what it means to be a limiting point. So what is a cluster point? No, this is what it means to be a limit. So what does it mean to be a cluster? So AN has a cluster point. AN has a cluster point B if so pay attention now to the quality, the quantifiers up here. So for any epsilon, you used to write exists, but now it's for any epsilon and for any n. Right, so we swapped the existence here to a for any, and then we're going to swap the for all to an existence. AN belongs to V epsilon of A. So you give me any ball, then no matter how big a number you come up with, I can find an even bigger number such that I belong to the ball. The language here is that AN is infinitely often, so that's the new word, infinitely often in any ball around A. And so what we're seeing in the example, with -1 and 1, right? If this is my ball around -1, and this is my ball around 1, we see that we do not converge to 1 and -1 because we keep jumping behind back and forth. But what is true is that no matter how far out in my sequence I go, I always get into both these. So no matter how far out for any n, right? So no matter how far out you go, I can always find a point that comes later, such that I'll be in this ball and such that I'll be in this ball. So here both B equals to 1 and B equals to -1, they are clusters. And so the big theorem is, this is the Bolzano-Weierstrass theorem. Bolzano-Weierstrass. Bolzano-Weierstrass, it says that if AN is bounded, it has a cluster point. There is a cluster point. So equivalently, one can, instead of writing this cluster point equivalently, you can write that there is there's a subsequence A and K inside AN that converges. That's the big result of this section 2. How are we doing? You guys are not, are we all asleep, or does anybody have any questions or comments on what we've been doing? So we have 15 minutes left. The definition of a cluster point, yes. The definition of a cluster point. So you have your sequence. You have your sequence, and so what you want to do is you want to think about sequences that are not converging. Right? So you want to have something that is oscillating. So say that you would have what could it be? So you would have a point somewhere on the real line. So there's your point B, right? So your sequence could be it could be that it would go, you start out here, and then it could go up, and it could go down, and it could go up, and it could go down. So you could make these bounces, and the bounces could say oscillate, like sine x. So what I have sine sine of, what would it be? Something like so it's periodic with 2 pi, so 2 pi k. Sine at 0 is 0. Right. So how would this look like? You would run sine, and this would give you for so this will be periodic with I would put, maybe sine is a bad example. Like sine 1 over n goes to 0. This is going to oscillate. So where would this here would be a sequence of points. This would be a sequence of points inside the interval -1 to 1. Right? That's how it would have to be. This is sine n. This would be a sequence of points between -1 and 1. But if I try to look at the limit, right, so this is my an. There's no limit. Right? This limit, it does not exist. Right? Because it oscillates. But the way that it oscillates, there's some, it's periodic, right? So it'll revisit. Like, how would it look like on a picture? If I share my screen, maybe try Mathematica and see how would it look like if I were to go in here and say plot like sine n, and then n from, I don't know. There is some periodicity, right? So what kind of cluster points could this sequence here have? What did you think, Priya? What kind of a cluster point could this sequence here have? Yeah, all of it, exactly. Okay, so pick one. So let's try b equal to 1. Does this sequence here come along b equal to 1 infinitely often? So if I pick a neighborhood, so this was on the picture, right? So if I pick a neighborhood, right? So pick an epsilon. So this is my neighborhood over here in the top. This was equal to 1, and then I'll go down a little bit. So I have 1 minus epsilon here. This is my neighborhood. For this b to be a cluster point for that sequence of sign n here, what would have to happen is that this sequence would come into this neighborhood infinitely often. Right, so no matter how big a number I have, so no matter how big n is, no matter how big n is, an comes close to 1. What does it mean to come close to 1? Well, it means that an belongs to this interval 1 minus epsilon to epsilon. No matter how big n is, an comes close. So this is what that means. For some n bigger than capital N. So no matter how far out in the tail you go, you're always going to be coming into this neighborhood and any other neighborhood. Like if you have that property, it's a cluster point. That's right. You can have cluster points without having a limit. And evidently, right? Because evidently, right? This beast here, this sign n, there is no limit. But there are lots of cluster points. But if there's a limit, would there be no cluster points? Well, how many cluster points would there be? How many cluster points would there be? Yeah, the limiting point is a cluster point, right? Yeah, we're not demanding here that you hit the limit either, right? We're saying we're entering the neighborhood. Right? We're coming close to. We're not saying that we should, this should not be epsilon, this should be 1. We are not saying here that we should be equal to. We are not saying that we should be equal to. We are not demanding that an equals a b, but we're just demanding that we're close. Right, that's when I'm talking about entering. Right, we're just saying that we are in this neighborhood. We're not saying that the ANs should become A. Yeah, so being a cluster point is a weaker condition than being a limiting point. So there are lots of sequences out there that have cluster points, but they do not have any limit points. But what do you think about cluster points? If I have a cluster point like this one here with the sign, share the screen again. If I have a cluster point, so say take the cluster point to be 1 here, I don't converge to 1, but can I find a subsequence that converges to 1? right? So if you have cluster points, you can find subsequences that converge to those. And so that's the point of this Bolzano-Wallerstein theorem. It says that if you have such a set, if you have a sequence that's bounded, it's got to have a cluster point. And if it has a cluster point, I can create a subsequence that will converge to it. But we're almost out of time, so I don't want to rush through that theorem. This is a big gun, and I want to take my time doing that. Maybe we can do it on Wednesday when we're in class. No, that's not how it goes. Because like the number of subsequences with a limit. No, I don't think this is the same. Like for any cluster point, you are guaranteed that you can find one sequence, but you can potentially find many different sequences. You can always throw away the first elements in a sequence that doesn't affect what the limiting value is. So this is not one-to-one. For each cluster point, you can find at least one sequence, but potentially you can find infinitely many sequences that will go to infinitely many different sequences that will go to the same cluster point. Like in this example here with sine, we could do something like that. Like how would I, so we have agreed now on that this sine n has a cluster point, has cluster point b equal to 1, right? So you can find a sequence is sine of nk such that sine nk converges. I think I should write it down. So let me write it down with the natural number. So if I take sine of what is going to be something like pi over 2 plus 2 pi k, this would be 1. So this could be one of your sequences. This could be your sequence AK. That would converge. AK would converge to 1. But we can find lots of other ones, right? You can also have a BK that's equal to sine pi over 2 plus 4 pi k. These are always going to be equal to 1, right? So BK is also going to converge to 1, but you're not the same. So it's not the particular subsequence that is crucial. What is so the particular subsequence will typically not be unique. There'll typically be as many. There will be many different ways of approaching a given point. The thing that you're guaranteed is that if you have a cluster point, then you can approximate it. You can find a sequence that will converge to it, but you can find many sequences that will converge to a given cluster point. Like in here too, right? They're not the same. This one here picks off every other element in this one up here. Does that make sense? Okay, I think it's time to call it quits. Are there any other questions or comments? I should say that so we have office hours. Office hours are on Thursday mornings from 11 to 12. I posted a document that listed them on a Tuesday, and this is not good. It's on Thursday mornings with me from 11 to 12. And then on Canvas, you can see when the TA has his office hours. Are there any questions or comments before we wish each other a good weekend? If not, I'll see you on Wednesday.